So for our next problem, the, we're going to get the value of e raised to negative 80 cosine bt into the complex frequency function, which we will be using the Laplace transform. So the Laplace transform of e raised to negative 80 cosine bt is equal to the integral of e raised to negative st multiplied by e raised to negative 80 multiplied by cosine bt dt. Where here we have the same base, so we're going to apply the law of exponentials. So adding the exponent and you're having the same base. So simplifying this equation, which will lead us into the integral of e raised to parenthesis of negative s minus a of multiplied by t cosine bt dt. So equivalent to the, we will remove the negative signs inside the parenthesis of s plus a of negative s minus a, so it will be equal to the integral of e raised to negative parenthesis s plus a parenthesis t multiplied by cosine bt dt. So as you can see in this expression, we could solve this expression using integration by parts. So let our u as cosine bt, du is equivalent to the derivative of cosine bt is equal to the negative b sine bt dt. Our dv is equivalent to the e raised to negative of parenthesis s plus a parenthesis t dt. So the v will be equal to negative 1 over s plus a multiplied by e raised to negative parenthesis s plus a t. So by plugging in the variables or the designated values of this in the formula of the integration by parts, which is the uv minus integral of v du. So negative cosine bt over s plus a multiplied by e raised to negative parenthesis s plus a t approaching 0 to infinity minus b over s plus a integral of e raised to negative parenthesis of s plus a t sine bt dt. So as you can see, we're going to plug in these limits in this equation, or we're going to evaluate this. So as you can see, at our limit, when our limit is an infinity or any large number, so any value that has a negative high numbered exponent is equal to 0. So minus the cosine b times 0, which is equal to 1 over negative, which will be equal to negative 1 over s plus a, and e raised to negative s plus a multiplied by 0 is equal to e raised to negative 0, e raised to 0, so equal to 1. So the answer would be negative 1 over s plus a. So by copying this one, so this our next equation is 0 minus the negative 1 over s plus a minus the b over s plus a multiplied by the integral of e raised to negative parenthesis s plus a t sine bt dt. So another integration by parts. So let our u would be equal to sine bt, and the derivative of sine bt would be b cosine bt dt. And the dv would be the same, which is equal to the e raised to negative parenthesis s plus a multiplied by t v, and the value of our v is equal to the negative 1 over s plus a multiplied by e raised to negative parenthesis s plus a t. So plugging in again the values of our variables using the formula of integration by parts. So this is the equation we have come up. So the negative of e raised to negative s plus a t sine bt over s plus a approaching 0 to infinity plus the b over s plus a multiplied by the integral of e raised to negative s plus a t cosine bt. So here we're going to plug again our limits. So again, we're going to have a zero value here because of when if you substitute the infinity in here in the exponent, which is have a negative value, would be equal to 0. While here, so if your sine bt or sine b is times 0, which is sine 0, it's also equal to 0. That's why the equation is 0. So we conclude that would be equal to, this one is equal to 0 by plugging in those limits. So our variable steps are 1 over s plus a minus b plus a multiplied by the positive b over s plus a multiplied by the integral of e raised to negative negative parenthesis s plus a multiplied by t cosine bt, which is our first expression. So I forgot that if we let this one as our y, so be equal to y is equals to the equation of this. So we can let this one be our y, and here's our, so let y is equal to the integral of e raised to negative st multiplied by e raised to negative at cosine bt, or simply the integral of e raised to negative s plus a t cosine bt dt. So plugging in y is equals to, which is the Laplace or the integral of e raised to negative s plus a t cosine bt dt is equals to 1 over s plus a minus b plus b over s plus a multiplied by the 0, which is here, and plus the b over s plus a times y, which is the value of y, that e raised to negative s plus a t cosine bt, which our repeating integral. So by distributing this b over s plus a, we would come up at y is equal to 1 over s plus a minus the b squared over s plus a squared multiplied by y. So we're going to transpose this one, the negative b squared over s plus a squared y, into the left side. So we could come up in this expression, which we're having which we will be finding the LCD, or the least common denominator, which is the s plus a squared. So we're coming up with the s plus a squared plus b squared over s plus a squared y equal to 1 over s plus a. Now, you're wondering why we come up with this expression, or the final answer. Here how it happens. So if you transpose this one into this side, would be y equal to 1 over s plus a multiplied by the s plus a squared over s plus a squared plus b squared. So cancel, so the left will be s plus a over s plus a squared plus b squared. So the final answer for that is this, or the equivalent of the Laplace of e raised to negative at cosine bt is equal to the s plus a all over s plus a squared plus b squared. And that is the value of our time function e raised to negative at cosine bt in the complex frequency function.